Till now we have been looking at one-dimensional problems. We looked at the linear harmonic oscillator, also at the square well potential. Now, in all those cases, we could identify a length factor, a length, an object of the dimensions of length, which I could make with the parameters available in the problem. Now, you will recall that in the case of the linear harmonic oscillator, we had root of h cross by m omega, and that had the dimensions, that gave us the dimensions of length. Similarly, in the case of the square well potential, the potential itself was non-zero from minus a to a. So, x taking values minus a to a, v was minus v naught, and therefore, I had a length scale which was naturally there in the problem, and that is needed in order to have a bound state. The surprising thing about quantum mechanics, as I have also reiterated in the past, is that there are classically forbidden regions which are accessible to the quantum state. For instance, in the case of the harmonic oscillator, if you had plotted v of x versus x, now that was a parabola going all the way up, and a classical particle would be confined to this region. In fact, a classical oscillator will go there for a given value of energy. The classical oscillator goes there, that is a turning point, turns back, comes here, that is another turning point, and does the oscillation like this. But as you know, even in the ground state of the harmonic oscillator, the wave function is a Gaussian, and therefore, the Gaussian dies down only at large x. So, the probability of seeing the object away from the potential, outside of the potential, is also non-zero, and therefore, classically forbidden regions are accessible. Similarly, in the case of the square well, the particle which was confined to the square well could well have a non-zero probability of being outside the square well. So, this was the surprise, one of the surprises from the quantum version of these problems. Today, I would like to look at three-dimensional problems. The simple example that we can talk about is the case where there is a central potential. So, if the potential V is simply a function of r, and I have used spherical polar coordinates, an example could well be the Coulomb problem, where the potential is minus Z e squared by r. So, we look at situations like this, where we will be dealing with the central potentials, a three-dimensional problem. For instance, the hydrogen atom, where there is a proton in the nucleus and an electron outside of the nucleus. So, such problems would show a certain amount of symmetry, because if the potential is central, then you know that orbital angular momentum is conserved. L squared, the angular momentum operator square, is the generator of space rotations, and therefore, I would expect that if L squared, the operator, were written in spherical polar coordinates, it would merely be a function of theta and phi. We can write L squared in terms of theta and phi, and not r, as a differential operator involving delta by delta theta and delta by delta phi, and not the radial coordinate. The problem that I want to solve is of course an eigenvalue problem, which is minus h cross squared by 2 m, generally a particle of mass m, del squared psi of r theta phi this is the p squared by 2m part plus v of r psi of r theta phi is E psi of r theta phi. So, instead of writing psi as a function of x, y, z, I write it in terms of r theta and phi. What I want to check is the following thing. Del squared of course can be written in spherical polar coordinates in the following manner. Of sine theta delta by delta theta plus 1 by r squared sine squared theta delta 2 by delta phi squared. You will recall that in spherical polars the scale factors are 1 r and r sine theta, and that is why I have put them out here. That is a 1 here and an r squared there and r sine theta the whole squared here. Those are the scale factors when I go from Cartesians to spherical polars. So, this is del squared, and since L is r cross p, which is minus IH cross r cross del, L squared would be r cross p dotted with r cross p and will therefore involve del squared. So, I would like to write del squared, I would like to write a relation between del squared and L squared. Now, if I did that, I can replace del squared, re-express del squared in terms of the radial part 1 by r squared delta by delta r of r squared delta by delta r plus an angular part which will depend only on L squared. When L squared acts on psi, it is obviously going to change only the angular part of the wave function, because angular momentum is the generator of space rotations, and that will only involve the angular coordinates. And therefore, it would be possible to try to do a separation of variables here and write psi of r theta phi as r of r, some chi of theta phi, so that L squared acts only on chi of theta phi. The equation would then separate into a radial equation, differential equation, and an angular differential equation. We will be solving for the eigenvalues and eigenfunctions of L squared. We will use that as an input in this equation, and we will solve for the eigenvalues of del squared. So, that would be the procedure that we will adopt in this problem. In order to write del squared in terms of L squared, I need to do a little bit of algebra. First of all, I consider r dot p the whole squared minus r squared p squared. This is a straightforward exercise, but it is worth going through it so that we understand that things do not automatically commute with each other, and we put in the appropriate factors which arise because of non-commutativity in quantum physics. So, this object is xpx. So, when I expand this, this gives me xpx xpx that comes out of using terms like this, and from this I subtract x squared plus y squared plus z squared times px squared plus py squared plus pz squared. Now, it is clear that if I commute x across px, using the fact that the commutator of x with px is IH cross, I get a term x squared px squared, similarly a y squared py squared here and a z squared pz squared there, and that will cancel out with x squared px squared plus y squared py squared plus z squared pz squared here. So, I will be left with terms from here which involve IH cross. So, use the commutator, XPX is IH cross, similarly for Y and PY and Z and PZ. So, PXX is XPX minus IH cross, and therefore, what I will be left with here is minus IH cross XPX minus IH cross YPY minus IH cross ZPZ, which is minus IH cross R dot P. So, therefore, I have R dot P the whole squared minus R squared P squared is minus IH cross R dot P. All these terms continue to survive up to this point. As I have already told you, x squared px squared cancels out from here after putting in the commutation relation, and therefore, I am left with minus x squared times py squared plus pz squared, that is the first term. Similarly, plus there is an overall negative sign. So, minus y squared times px squared plus pz squared minus z squared times px squared plus py squared. So, I am left with this. Now, once more I can do the following. I can write here ypy as pyy plus ih cross and this as pzz plus ih cross. Similarly, here this would be pxx plus pzz plus 2ih cross. Here too pxx plus pyy plus 2ih cross. And therefore, this simplifies to the following. Look at this, 2ih cross xpx plus 2ih cross ypy plus 2ih cross zpz, which is 2ih cross r dot p minus ih cross r dot p. So, that just gives me ih cross r dot p. And then of course, I have the following things left behind, pyy plus pzz out there plus zpz times pxx plus pyy plus ypy times pxx plus pzz. And then of course, I have to subtract out these things, minus x squared py squared plus pz squared minus y squared px squared plus pz squared minus z squared px squared plus py squared. So, this is what I have. Look at these terms, compare this with an object like L squared. So, let us look at L squared now. L squared is R cross P dotted with R cross P. Of course, you will be able to write this as, if you now compare term by term, you will find, for instance, look at this term, there is an x, px, py, y, and out here you would see the same kind of term that appears. There is an x, px, py, y. The order is right because px can be commuted across y and py. So, this is a minus x, px, py, y, and here I would have plus x, px, py, y. You can compare it term by term and you find that what occurs here, out here, apart from ih cross r dot p is minus L squared. And therefore, this object r dot p the whole squared minus r squared p squared is I h cross r dot p minus L squared. And now I move on to spherical polar coordinates. First of all, I write p as first of all I write r as r E r and p as E r delta by delta r plus so on, apart from minus I h cross, which we should remember to put in. But what matters in r dot p is simply r delta by delta r, and therefore I have r delta by delta r times r delta by delta r, that is the first term, minus r squared p squared is I h cross r delta by delta r minus L squared. So, this is the kind of thing that I have, but p squared itself is minus I h cross del the whole squared. So, let me put that down here. Therefore, I have r delta by delta r times r delta by delta r minus r squared times minus I h cross the whole squared del squared is equal to I h cross r delta by delta r minus L squared. This can be easily done now to say that L squared can be written in terms of del squared, or perhaps I should just write del squared in terms of L squared. So, I have r squared h cross squared del squared from here is I h cross r delta by delta r minus L squared minus r delta by delta r of r delta by delta r. But I can now write del squared in spherical polars, and that expression is given here. I substitute for del squared from here, and then if I check by putting things in, substitute for del squared here, I can show that del squared is 1 by r squared delta by delta r of r squared delta by delta r, the radial part survives, minus L squared by h cross squared r squared. The h cross squared, because we know that angular momentum occurs in units of h cross, and therefore this should carry dimensions h cross squared. So, I scale that out, and 1 by r squared, there is a dimension matching. Del squared has dimensions of 1 by r squared, and that is what happens here. The minus sign is simply kept from here. I have merely substituted for del squared from there, and this becomes an important relation between del squared and L squared. So, this is one way of seeing it. I could have done it by moving on to spherical polar coordinates right at the beginning, could have done it in different ways. It is straightforward algebra, but the result is worth demonstrating, because as a matter of exercise, it teaches you that right at the very first step, you cannot simply interchange p x and x any way you wish, have to use the commutator relation and maintain order of things. So, this is what you get for del squared. So, now let us go back to the eigenvalue problem. The problem that I have is minus h cross squared by 2m del squared psi of r theta phi plus v of r psi of r theta phi is E psi of r theta phi. So, this is what I have. I substitute for del squared. Therefore, minus h cross squared by 2m. I should say what this m is all about. Suppose we were looking at the hydrogen atom problem, for instance. Then there is this proton, it is a two-body problem. There is a proton and there is an electron. But instead of this two-body problem, I could go to an effective one-body problem where there is an origin of coordinates and there is an object here with mass, an effective mass mp me by mp plus me, which I can call mu or m, at a distance r, where r is the radial coordinate. So this is the equivalent one-body problem. As you know, you reduce a two-body problem to an equivalent one-body problem where this radial coordinate is from the origin of coordinates and there is a mass here, a reduced mass, which is mp me by mp plus me, if we are talking about the hydrogen atom. Otherwise, of course, any two objects with masses m1 and m2 would mean m1 m2 by m1 plus m2. So the m that I write here is essentially this reduced mass, perhaps I can call it m. But you should remember that by m I mean the reduced mass in the equivalent one-body problem. So that is what we have here, and in that picture I can now substitute for del squared as 1 by r squared delta by delta r of r squared delta by delta r minus L squared by h cross squared r squared. This acts on psi of r theta phi plus v of r psi of r theta phi is equal to E psi of r theta phi. This is the eigenvalue problem that I am out to solve. It is now clear what del squared is, what L squared is. Just by identification from here, I can write L squared, and therefore L squared is minus h cross squared r squared times 1 by r squared sine theta delta by delta theta of sine theta delta by delta theta plus 1 by r squared sine squared theta delta 2 by delta phi squared. Can cancel r squared, and therefore I only have an angular dependence in L squared, as I would expect. So this is the expression for L squared in spherical polars. I can see that L squared depends only upon the angular variables and is essentially the angular part of del squared. That is what this equation tells me. So when del squared acts on a wave function, which is a function of r theta and phi, this part of del squared acts on the radial wave function and this on the angular part of the wave function. In other words, I can try a separation of variables and write the total wave function as r of r some chi of theta phi. Now if I did that, I have the following equation. So this is what I have in my equation, and if I write psi of r theta phi as r of r chi of theta phi, so I can do a separation of variables. I will demonstrate that later, perhaps in my next lecture, but right now it is clear that chi of theta phi is an eigenstate of L squared after the separation of variables is done. So let me solve for that eigenvalue equation. I can write L squared, which is an operator function of theta and phi, acting on chi of theta phi is lambda h cross squared chi of theta phi. In fact, if you look at the structure of L squared, you can see that a further separation of variables can be done. And I can in fact write chi of theta phi as some theta of theta phi of phi. I'll put this into L squared, into this equation, eigenvalue equation for L squared. Substitute for L squared in terms of theta and phi explicitly. I can do a separation of variables. I'll demonstrate that in detail in the next lecture. But right now, I want to point out that after that is done, the equation for phi of phi would turn out to be this. Going from there to this step would be shown in a subsequent lecture, as I said, but this would be the phi equation, and I want to focus attention on this for a considerable part of this lecture. What appears here is the separation constant that you would have when a function of theta is equated to a function of phi after you do a separation of variables. So this is the separation constant. The solution for phi of phi is therefore e to the I m phi, m taking value 0, plus minus 1, plus minus 2, and so on. I want to make an observation here. The fact that m takes these values, the fact that lambda should be of the form L times L plus 1, simply because this is the orbital angular momentum operator, and it's orbital angular momentum operator square, and therefore its eigenvalue should be like, in pattern, should be like the eigenvalues for the spin squared operator, S squared. So the fact that lambda can be written as L times L plus 1 and m takes values like this would restrict L, and I will comment about this in the next lecture. But having said that, let me focus on this equation. The wave function should be single valued at any physical point, and therefore phi of phi plus 2 pi must be equal to phi of phi. What does that mean? E to the I m phi plus 2 pi is e to the I m phi, which implies that m takes these values. So that's how I get quantization of m. mh cross actually is the eigenvalue for Lz. But the important thing is that the quantization comes because of single valuedness of the wave function at a physical point. This is like a phase, and therefore phase changes of 2 pi m is allowed. There is a certain arbitrariness in the phase of the wave function up to 2 pi m, where m is an integer. But that's all. That's all the arbitrariness that's allowed. I now want to expand on the phase of the wave function, particularly in the context of a very important, enlightening, and certainly a very extraordinarily educative paper. And this was by Professor Dirac in 1931 in the Proceedings of the Royal Society of London. What Dirac showed in this paper was that quantum mechanics does not preclude the existence of isolated magnetic charges, like you have electric charges, which are integer multiples of E or multiples of E. Dirac showed that in quantum mechanics you can also have magnetic charges, and they will be quantized in units of
some G, which is the magnetic monopole, a monopole which is an isolated magnetic charge with magnetic charge G. Now, in order to get to that result, what Professor Dirac did was to talk about the change in phase of a wave function, the fact that things should be single valued at a given space-time point, and so on and so forth. With very little formal mathematical equations, but with extraordinary logic, deductions have been made in this paper on the magnetic charge, the isolated magnetic charge, and the quantization condition referred to as the Dirac quantization condition. So, let me now talk about some of the highlights of that paper and sketch for you how exactly that result was obtained. The Maxwell equation in the presence of electric charges reads del dot E is rho by epsilon 0. In the absence of magnetic charges, or in the absence of monopoles, magnetic monopoles, we would have an equation like this. Of course, if you had magnetic charges, you should put a rho sub m here, analogous to the rho that we wrote there. This is what you would have in the absence of magnetic monopoles. In order to worry about whether a monopole exists or not, let us follow Professor Dirac's logic. Suppose I have a point A in space time. So, the coordinates are x, y, z and t, and I have a wave function psi, which is of course a function of x, y, z and t. This wave function satisfies a normalization condition psi star of x integral psi star psi over the volume is 1. So, that allows for a phase in psi. So, instead of psi, I could have well written psi e to the I alpha, then psi star would be psi star e to the minus I alpha, and the normalization condition is still satisfied. So, there is a certain arbitrariness in the phase of the wave function. Now, suppose the system moves from point A to point B. Notice that here psi is a function of x, y, z and t, and therefore, I can write this as some psi 1 of x, y, z, t e to the I alpha of x, y, z, t. So, there are two objects here which change in space time, and when you go from A to B, what you can measure is the change in phase of the wave function, because the phase changes with space time points. So, while absolute phase is arbitrary, there is a certain arbitrariness in the phase. Phase differences between two neighboring points, phase difference in the wave function is not arbitrary, and in general it can be non-zero. Now, suppose you took the wave function from A to a somewhat distant point B. Clearly, you can think of it as being made up of small paths which take you there. But since the phase changes from point to point, the net change in phase delta alpha is going to depend upon the path that is taken. Over each of these paths, delta alpha is going to be different, because alpha itself varies from point to point. Therefore, we have the following conclusions. There is an arbitrariness in the absolute phase of the wave function, but phase differences which are path dependent appear when moving from A to B. And therefore, when one goes from A to B and comes back from B to A over a closed path, we need not expect the net phase to be 0, because this is a certain path and the total phase accumulation on this path need not cancel out the phase accumulation on this path. So that is what I meant by a path dependent phase difference. On the other hand, we know that if you have a wave function psi and another phi, this object is the overlap between psi and phi. And in fact, when mod squared, it tells me the probability of agreement of the two states psi and phi, and therefore that is unambiguously fixed for a given point, which means that the change in phi over a closed path from A to B and back to A, the change in phi should be equal to the change in psi, so that you see this is psi star phi, and since it is a phase change, it comes as e to the minus I alpha here and e to the plus I alpha there, or vice versa, and cancels out. So the change in the phase of a wave function after traversing a closed curve should be independent of the wave function itself. It should be the same for all wave functions. Change in phase of a wave function over a closed curve is independent of the specific wave function. If you go back to this example, that is the kind of thing that is being told. The change in phase has to be integer multiples of 2 pi, so that there is single valuedness of the wave function, and so on and so forth. But now that is because of an arbitrariness in phase. I am now talking about a different issue. How could this change in phase of the wave function, how could it have happened? It could happen for the following reason, and that is what I will illustrate now. Let me start off in general by writing a wave function as some psi 1, and any change in phase happens because of psi 1 of x, y, z, t, and any change in phase which I am going to add up here and call it e to the I beta. Then suppose I consider the x component of the momentum operator px psi. In quantum mechanics, this is minus IH cross delta by delta x psi 1 e to the I beta, and that object is minus IH cross delta psi 1 by delta x e to the I beta plus I psi 1 delta beta by delta x e to the I beta. Similarly, I can write down expressions for py psi, pz psi, and also e psi, similarly for py psi. These are operators, pz psi, and e psi is IH cross delta by delta t psi, psi 1 e to the I beta, and that quantity is IH cross delta psi 1 by delta t e to the I beta plus I psi 1 delta beta by delta t e to the I beta. Now, since the wave function is continuous, the derivative of beta, the phase, should exist, and I am going to refer to as delta beta by delta x as kx, delta beta by delta y as ky, delta beta by delta z as kz, and by k naught I refer to delta beta by delta t. So, this is what I have when I work with the momentum and the energy operator on psi. So, let me look at the structure. Px psi is simply minus IH cross. I can write this as Px psi 1, because minus IH cross delta by delta x psi 1 is Px psi 1. There is an e to the I beta anyway, and then I have plus h cross psi 1 kx. So, I can also pull the psi 1 out. E to the I beta is here, and I can write psi 1 like this. Similarly, Py and Pz, which tells me that if I define an object k which has components k naught, kx, ky and kz, and a 3 vector k which I will refer to as k with components kx, ky and kz, then definitely this is true. P goes to P plus h cross k. Similarly, E goes to E minus h cross k naught. What does this mean? This is how psi 1 behaves when I write psi as psi 1 e to the I beta. So, whenever there is a wave equation which involves the momentum operator P and the energy operator E, and if that wave equation is satisfied by psi, psi 1 satisfies the corresponding wave equation with these replacements. Let us put that down here. So, if psi satisfies a wave equation involving P and E, these are operators, remember. Psi 1 satisfies the corresponding wave equation with P going to P plus h cross k and E replaced by E minus h cross k naught. But this is very reminiscent of something that you know. When you learnt about gauge invariance, gauge theory and so on, you realize that when a charged particle is put in the presence of a homogeneous magnetic field, there is a minimal coupling that happens between the charged particle and the field. The minimal coupling prescription was like this, except that if the vector potential was A, P was replaced by P minus EA by C, and E was correspondingly replaced with the scalar potential. So, given a vector potential A and a scalar potential phi, this change, this replacement is very reminiscent of what happens when a charged particle is put in the presence of a homogeneous magnetic field. Now, by sheer identification, I know that A can be written as h cross c by E k. Similarly, phi can be written in terms of k naught, but this is of relevance to me right now. So, A is minus h cross c by E k. What does that mean? I can define a magnetic field B, which is del cross A, but I also know that if there is, from where does this field appear? Let us imagine that this field is because of a non-zero isolated magnetic charge, and let us say the strength is G, sitting somewhere in space. So all I am doing now is to take a wave function of a charged particle over a circle. And what is the change in phase of the wave function? The change in phase of the wave function can be written as delta beta, and delta beta is simply integral over the circle, let me call that C, of k naught dt plus kx dx plus ky dy plus kz dz. So if I defined a k which had components that I have put down here, and I define a dl which has components dt, dx, dy and dz, then in the notation used by Dirac in his paper, this would be the line integral of k. But this delta beta, because I know that delta beta is this object, and that is how I got that expression, because kx is this and ky is that and so on. But I also know from Stokes' theorem that I can write this object as an integral over the surface that it encloses, the surface that it bounds, of del cross k ds, again in the notation used by Dirac in his paper, because this is like the line integral related to the surface integral, Stokes' theorem, and ds is the surface that I am talking about. So this is what I have, and this object is delta beta. But I also know the following. I know that this is the flux due to this charge that is sitting there, because del cross k is like the magnetic field, and when I do the surface integral, it is the flux. And analogous to Gauss's theorem in electrostatics, since G is a constant, this flux is going to be equal to 4 pi G. If I had a charge Q, it would have been an integral over the surface of the field due to this charge, and analogous to that I have 4 pi G here. Now let me examine the various surfaces that are possible here. Consider, for instance, the limiting case, which is of interest to me, when the line integral itself, when the curve that bounds the surface shrinks to a point because the surface becomes a closed surface. So it just shrinks to a point. Then I know the following. This integral goes to 0 because dl is 0, but on the other hand there is a non-zero magnetic charge there, and therefore the flux is non-zero. If the flux is non-zero, the only way by which I can have a non-zero quantity with this whole thing going to 0 is if B becomes singular at that point. And therefore I have a magnetic field which picks up a singularity at one point on the closed surface, and suppose the closed surface is simply the point G itself. If the closed surface is shrunk, then I can well imagine that there is a singularity of the magnetic field at the monopole site. So I have a singularity of B at monopole site, at the monopole site. That is one aspect, that if I define a B, I can still get away with it, provided I have a singularity at one point on any closed surface around the magnetic charge. which I consider here. Now, more to the point, if the line integral, if the line is the curve is simply reduced to a point, there is nothing like a delta beta. Delta beta is 0 because I never really went over a path to accumulate a phase. In fact, there is no movement, it is simply a point. So, let us consider the case of non-traversal, if I may use the word, of any path. In other words, at any physical point, delta beta is equal to 0. There is no phase accumulation because no path was traversed. As a digression, I should say that if you did traverse a path and somehow accumulated a phase, that too can happen in certain contexts, and the Berry phase is an example. I will comment about it later. But returning to this, as it is, there is an arbitrariness in the phase of 2 pi n. In my earlier example, I called that m, the magnetic quantum number, 2 pi m, but now I am referring to it as 2 pi n, where n is an integer, 0, 1, 2, 3, anything plus minus 1 and so on. We have to put in that arbitrariness plus pi g, but it is not just 4 pi g because this is del cross k, and therefore in terms of A, and this is not quite the flux, I should be able to write this k as EA by h cross c. So, I have an EA by h cross c, E by h cross c multiplying A. Instead of k, I write it as EA by h cross c, and this is in fact the magnetic field. So, I have a constant E by h cross c to reckon with. So, it is 4 pi g E by h cross c. So, look at a situation when delta beta is 0. What does that mean? Let us set n equals 1, that means I am talking about a fundamental pole analogous to E, the electron's charge. So, 2 pi is equal to minus 4 pi E g by h cross c. So, I have E g by h cross c getting quantized now because E g by h cross c is now equal to half. I have set n equals 1, otherwise I will have an n by 2, and suppose I look at this as the electron's charge. So, if I am talking about an electron, so I would have had a minus E and that would have cancelled the minus sign here. So, in fact, I just have E g by h cross c equals half. Suppose by this I meant the electron's charge. Therefore, I have E g by h cross c is half, or E g is h cross c by 2. But E squared by h cross c is a very small number, it is 1 by 137. So, substituting for h cross c into the Dirac quantization condition, that is E g is equal to h cross c by 2. Into that, if I substitute for h cross c, I find that g is very large. G is 137 by 2 E, and that is a large number. And therefore, not that quantum mechanics precludes the existence of isolated monopoles. We have just now gone through the entire machinery as proposed by Dirac. However, it is very difficult to isolate a monopole because monopoles are very strongly interacting with each other, very strongly coupled to each other. So, these are the contents of the significant part of the contents of the paper by Professor Dirac in the Proceedings of the Royal Society. Quite apart from what I have told you here, there is another matter that comes out very clearly, and that is this. If there is a method of producing a net change in phase, apart from the arbitrariness 2 pi n, which I will not talk about really, that change in phase should come because of effectively a field sitting in the appropriate space. In this case, we are talking about the change in phase in physical space when a wave function goes around, and that is where the single valuedness of the wave function came into effect. However, in a general setting, the change in phase would really appear because of an effective field of force in an appropriate space, and that is what happens in the case of the Berry phase. This is very interesting, again very useful and important seminal paper by Professor Berry. I have the reference here. It's M.V. Berry, Proceedings of the Royal Society of London again, and this is volume 392 in the year 1984, page 45. Now it led to an explosion of papers, but before I talk about some of them at least, or mention some of them at least, I want to point out how exactly the Berry phase appears. The Berry phase, as it is called, it's clear that it comes because of dynamics, because earlier on I told you that all wave functions pick up the same phase when they come back to a physical point, but there could be a small change in the statement if there is an effective field sitting in the space. For instance, suppose I am able to change the parameters in a Hamiltonian. Take for instance the simple harmonic oscillator. Certainly one parameter is omega. Suppose I cycle omega slowly over time and then get back to the original value of omega. In general, there can be more parameters. So in a parameter space, which is appropriate for that given physical system, if I did an adiabatic slow cycling of parameters and brought them back to their original value, Hamiltonian cannot change, it's physically measurable, but then the wave function can pick up an extra phase, and that is called the Berry phase. The Berry phase could be different for different wave functions, simply because their dependence on the parameter, each wave function depends on the parameters differently. The Berry phase itself is experimentally measurable in certain settings, because I could have a handle on the parameters and the way I cycle the parameters. While the original work done by Professor Berry talks about adiabatic cycling of the parameters, and therefore there is a monopole sitting in the parameter space now, not in physical space, that has been relaxed, and in a very general setting where the cycling need not be adiabatic. In fact, it need not be over a closed path, it can even be over an open path. Generalizations have been done. There are many papers dealing with that, but I mention one of these papers by Professors Mukunda and Simon. This was done in 93. There have been many names associated with the Berry phase and its classical counterpart. The Hane angle is a classical counterpart. The Berry phase in the context of optics is a Pancharatnam phase, and subsequently many other names have been associated with it. I have put down some of these names, and in fact this is an extremely partial list of names. But for those of you who are interested in knowing something more about the Berry phase, there is this book, Geometric Phases in Physics, edited by Chaper and Wilczek, and I should also include their names here in this list. There are many more names. This is to be treated completely as a very, very partial list of people who have worked on Berry phases, and in general it is clear that phases are very important. Some of them are experimentally measurable, and one cannot just very casually put aside a statement like the wave function is single valued up to an arbitrary phase. It is not just an arbitrary phase, you can generate more components to the phase, like the Berry phase or like the phase that led to the monopole quantization. In the next lecture, I will continue where I left off with orbital angular momentum, work out the details of the separation of variables, and we will take it up from there.